Part 1, the bedrock principles of programming and computer systems.
The fundamentals.
To kick us off, we're starting with the absolute bedrock. I mean, before you can effectively tell an AI to build anything complex, you really need to grasp the fundamental physics of computation, right?
You have to. You need that grounding.
This section is all about those foundational rules of programming and how computers actually execute instructions. First up, a book by the creator of C++ himself, Bjarne Stroustrup. It's programming. Principles and practice using C++. Now, this isn't just a language manual. It's a really deep dive into the principles of programming,
Yeah, it's much more than syntax.
focusing on writing useful, correct, maintainable, and efficient code through concepts like type safety and resource management.
And that's crucial because even as AI generates C++ code, it's often trained on this vast ocean of human-written code. Some of it's great.
But a lot of it probably isn't.
A lot of it is, well, mixed quality or outdated. This book teaches you modern C++ principles like RAII, resource acquisition, is initialization.
RAI.
Essentially, it's a C++ idiom. It makes sure resources, like memory or file handles, are automatically released when they're no longer needed. No leaks.
Ah, okay.
It shows the why behind using things like std.uniqueCapturedPars, that's a smart pointer, that manages memory for you instead of raw pointers. Raw pointers are something an AI might frequently generate, leading to common issues like memory leaks and security vulnerabilities.
Right, the classic pitfalls.
And AI can certainly write the code, but this book gives you the wisdom, the judgment to make it trustworthy and secure.
But, I hear a lot of chatter, especially on social media, saying C++, it's too hard, it's outdated. AI can just write it for me now, so why bother?
Yeah, I've heard that too.
That feels like a dangerously short-sighted view to me.
It really is. C++ remains the backbone of high-performance computing. That includes the very AI frameworks and models we use every day.
So what happens if you rely on AI for critical C++ components without truly understanding its principles?
Well, it's like asking a translation app to write a legally binding contract.
Ooh, yeah. Bad idea.
It'll probably miss the critical nuance, maybe introduce catastrophic errors. In practice, you might prompt an AI, generate a C++ class that reads data from a network socket. Okay, fine. Then you, armed with Stroustrup's principles, perform what I'd call a principles-based code review.
Okay.
Does it use raw pointers? To refactor it with std.uniqueCaptr for RAII. Does it use generic void pointers? You refactor for type safety using templates.
Got it.
This transforms the AI from just a black box spitting out code into, well, a powerful, maybe junior pair programmer that you can effectively guide and correct.
That kind of knowledge creates a profound strategic advantage, doesn't it?
Absolutely.
While many will just use high-level languages to interact with AI APIs, you'll be able to work deeper down the stack, closer to the metal, building and optimizing the very infrastructure that powers AI. That, to me, is a career moat, something highly defensible against automation.
Couldn't agree more. It's about understanding the foundations.
Okay, next up, we have a classic, often just called CS.app. It's Computer Systems, A Programmer's Perspective by Randall Bryant and David O'Halloran.
Ah, foundational text for sure.
This book really demystifies what happens under the hood when your program runs. It bridges that gap between high-level code and the actual underlying hardware. It's all about writing better software by deeply understanding the system's architecture.
Yeah, and when we think about the bigger picture, AI and ML models, they are incredibly computationally intensive programs.
Hugely intense.
And they're ultimately constrained by the hardware they run on. CSAPP provides you with the mental models to diagnose performance bottlenecks in those AI workloads.
Okay, like what specifically?
Well, for example, understanding the memory hierarchy, the different levels of memory from fast CPU caches down to slower main memory and data locality.
How close data is stored together.
Exactly. That understanding can lead to orders of magnitude performance improvements when you're training large models just by structuring data to maximize cache hits.
A cache hit, meaning the CPU finds the data it needs right there in its fast local memory.
Precisely. Avoids going to slower memory. Or, another thing, knowing about floating point arithmetic reveals how tiny, subtle rounding errors can sometimes cause model instability. That's critical in numerically heavy AI tasks.
Right. But the prevailing myth I often hear is, oh, my framework or my cloud provider, they abstract all the low-level stuff away, so I don't need to know it.
Yeah, that's a common one.
But abstractions aren't magic, are they? When an AI model trains inexplicably slowly, an AI code assistant isn't going to tell you, hey, your data loading pattern is causing excessive cache misses.
Exactly. It just doesn't have that physical context. Diagnosing and fixing that requires a human who understands that fundamental hardware-software interface. So to apply this daily, imagine you're optimizing an ML data pipeline. You use an AI maybe to generate an initial Python script.
Okay, standard starting point.
But if it runs slowly, you use profilers, sure. But then you, with that CSAPP knowledge, you ask deeper questions. Is it compute bound, limited by the CPU speed? Or is it memory bound, limited by data access speed?
Hmm.
How is the data actually structured in memory? This leads to informed refactoring, like maybe using a column-oriented format like Apache Arrow for contiguous data storage. An AI lacking that physical hardware model wouldn't typically suggest that on its own.
So in an industry where AI model training and inference costs are a huge
A
concern,
primary concern, yeah.
the ability to optimize performance is a genuine superpower. It transforms you from just an AI model developer into an AI systems performance engineer,
Huh.
making code run faster, cheaper.
It's a massive differentiator, especially as AI keeps driving more specialized hardware development. That expertise is gold.
Okay, moving on, we have The Practice of Programming by Brian Kernighan and Rob Pike.
Ah, legends. K&P.
Right. This book distills wisdom from these Unix pioneers, focusing on the craft of programming, writing code that's simple, clear, general, manageable, not just functional.
Yeah, and what's particularly insightful here, especially now with AI, is its focus on qualities that AI-generated code often, well, lacks.
Like simplicity and clarity.
Exactly. AI models optimized for functionally correct output, sure, but they have no intrinsic concept of elegance or readability. Their code can frequently be convoluted.
Hard to fault.
Very. This book champions clarity as fundamental. It gives you the toolkit to refactor and simplify that AI output, turning it from some opaque artifact into a genuinely maintainable asset. Principles like write clearly, don't be too clever. They're more relevant than ever when the machine you're working with is an AI that often prioritizes quantity or perceived performance over human comprehension.
But some might dismiss a book from 1999 with C examples as, outdated.
But the authors themselves explicitly teach universal engineering concepts independent of language. That's the key.
Right, and the idea that AI will handle this, it feels particularly weak here. AI can't generate a coherent style or design philosophy for a whole project, can it?
No, absolutely not. Without human guidance, an AI-assisted codebase just risks becoming this unmaintainable patchwork quilt of different styles and complexities.
Well, mess.
Precisely. Practically, this book guides that human-AI code quality partnership. Say an AI refactors a complex function for performance but makes it totally unreadable. You, applying Kernighan and Pike's principles, can pause and ask, is this optimization really worth the loss of clarity? Is it actually faster in a meaningful way?
Good question.
Then you reprompt the AI. Okay, prioritize readability now. Use clear variable names. You act as the essential design taste, the judgment layer, and the book's methodical approach to debugging and testing. That's a powerful antidote to the often black box nature of AI-generated code.
So as AI inevitably increases the quantity of code in our system,
As it will.
the demand for engineers who can ensure its quality is just going to grow exponentially.
Faster.
Mastering these principles transforms you into the editor-in-chief of your team's codebase. You're capable of guiding both human and AI contributors toward excellence. This craft of programming, emphasizing judgment and simplicity, that feels like a deeply human skill AI can't replicate.
I agree. It's about taste and long-term thinking.
Next, we explore Elements of Programming by Alexander Stepanov and Paul McJones. This one treats programming as a really rigorous mathematical discipline, building high-performance code on abstract algebra. It's about deriving general abstract algorithms.
Yeah, Stepanov's work is profound. Its ultimate focus on correctness and generality is fascinating. See, AI models generate code based on statistical correlation patterns they've seen. That's different from mathematical axioms that guarantee correctness across all possible inputs.
Okay.
Stepanov's philosophy teaches you to think about algorithms in terms of their essential mathematical properties. For example, that a parallel reduction operation like summing all numbers in a big list is possible and safe because the underlying operation, addition in this case, is associative.
Meaning the order you group things doesn't matter, like A plus B plus C equals A plus B plus C.
Exactly. That mathematical property allows for parallelization. This abstract understanding ensures solutions aren't just empirically correct for the cases the AI saw, but provably correct and broadly applicable. He introduces concepts as these formal specifications of requirements for generic algorithms. It's much more rigorous than just describing what a function does informally.
But I can hear the criticism now. It's too theoretical, too mathematical for everyday programmers. Or even AI could just generate the algorithm anyway. Does that really hold true considering what you just said about guarantees?
Not at all. That misses the book's core point. Mathematical rigor isn't just academic. It's a powerful tool for writing better, more reliable code. AI operates on correlation. It can't prove why an algorithm works. It can't formally define the minimal requirements for any sorting algorithm to be correct. This book gives you the intellectual framework to define those requirements formally as concepts.
So even if you're not proving lemmas every day.
Right, you probably aren't. But the thinking process is transformative. When you're designing a generic library, maybe with AI assistance, you might prompt the AI for a function to find an element in some container. But guided by Stepanov's thinking, you then pause and ask, what is the most general concept this algorithm can actually operate on? Not just a specific std.vector, but maybe any readable range defined by iterators.
Thinking more abstractly.
Exactly. You then refactor or reprompt the AI to be generic over iterator types, ensuring the resulting components are robust, reusable, and mathematically sound.
This mastery fundamentally changes how you see code. You move from thinking about just a series of steps to thinking about verifiable properties. That's the hallmark of a true software architect.
It really is.
This knowledge lets you design truly reusable APIs, contribute at a foundational level to core libraries, maybe even compilers, and lead technical direction with undeniable authority because you're reasoning from first principles.
That's the power of it.
Last, for this section, we have the definitive textbook on compiler construction, known everywhere as the Dragon Book. Compilers, Principles, Techniques, and Tools by Aho, Lam, Sethi, and Ullman.
The classic green dragon, purple dragon, depending on the edition.
Right. It gives this comprehensive overview of how source code gets translated into machine code.
So it's a great question. Why read a book about compilers now in the age of AI, especially with so many interpreted languages like Python being used?
Yeah, why bother?
The answer is that every single high-performance AML framework, whether it's TensorFlow, PyTorch, JAX, they all rely on their own sophisticated compilation stack internally. Understanding compiler principles gives you deep insight into how these frameworks actually achieve their incredible performance, from code optimization techniques like loop unrolling.
Doing more work per loop iteration.
Right. To the central concept of intermediate representations, or IRs. These are the abstract forms of code that compilers use internally before generating the final machine code. MLIR, for instance, is a modern multi-level IR used heavily in AI compilers today.
So knowing this helps you write better code even in Python.
Absolutely. An engineer who understands compiler principles can write Python or even JavaScript code that is JIT friendly, meaning it runs much faster because the just-in-time compiler can optimize it more effectively behind the scenes. You understand what patterns the compiler likes.
I could already hear some people saying, okay, but it's outdated or it's too theoretical because let's face it, most of us will never write a full compiler from scratch.
True, you probably won't.
So why invest that depth?
The value isn't necessarily in handwriting parsers, you're right. It's about understanding the underlying principles that make modern language runtimes work. Think about JavaScript's V8 engine with its JIT compilers. In your daily engineering, imagine optimizing an AI model for inference speed. You might use a specialized compiler tool like NVIDIA's Tensor. An engineer without compiler knowledge might just treat this as a complete black box. Press the button, hope for the best. But you, understanding Dragon Book principles, TensorArt is building a data flow graph internally and performing optimizations like operator fusion. That's where multiple small operations get combined into a single, more efficient one.
Ah,
So, if the results after compilation are incorrect, you can intelligently debug the process. You might suspect issues related to floating point precision changes during fusion, or maybe the fusion itself went wrong rather than just being completely baffled.
that makes sense. It gives you a mental model for debugging.
Exactly.
This expertise positions you right at that crucial intersection of AI models, software frameworks, and hardware, the absolute epicenter of performance optimization.
It really does.
It opens doors to highly specialized and probably quite lucrative roles in AI compiler development, performance engineering, maybe even hardware accelerator co-design. While AI can certainly assist in writing code, compiling that code efficiently for all the diverse hardware out there, that's becoming more complex, not less, making this foundational knowledge critical and, I'd argue, enduring.
Couldn't agree more. It's a deep skill.